Okay. Okay, let's start. Today's lecture would be about generative models. Okay. We are going to discuss two types of generative models. One of them is generative moment matching models, and the other one is adversarial networks, which is called GAN. So we will spend most of our time on GAN. It's very popular these days. But let me start with moment matching networks. So before I tell you about moment matching network, I need to tell you about basically, one measure of similarity between two distributions that we use in statistics, and is relatively recent. And it is used in this type of networks. The measure is called maximum mean discrepancy. Okay, so maximum mean discrepancy. It is pretty counterintuitive, but very interesting concept. Suppose that you have two distributions, distribution P and you have distribution Q. And you want to know how close these two are. So far, at least one way of comparing these two distributions. What is it? Scale divergence, right? So that's another measure. So suppose that I have sample from P, call it X, and I have sample from Q, call it Y, and say I have N samples here, and say I have M samples here. And my question is that how close these two distributions are. Maximum mean discrepancy, or in short they call it MMD, basically suggests that you can map these data through a phi, a transformation phi. So take X, apply some transformation phi to this, and you have phi of X. So do this for all of the points. Okay? Then take the average of these phi of X's. So I equal 1 to N of phi xi, 1 over N. This is the mean of phi of X's. Okay? Do the same thing for Y. 1 over M. Now, MMD claimed that the distance between distribution P and distribution Q is in fact, or can be measured as the distance between these two means. Sorry?
Fourier transformation.
Sorry?
This is Parseval's theorem of pure math. Yeah, in say the phi and the xi and phi are two transformations of P and Q. Then the distance of them are the same as distance between P and Q.
Right, but it depends on the type of this transformation, right? Not for any transformation, it's true. And it's not trivial, actually, because what we are comparing here is only the mean, right? So before applying this transformation, suppose that this is my P, and this is my Q. They have exactly the same mean, right? But they are very different distributions. How come just by comparing the mean of two distributions, you can say that these two distributions are the same? The idea is that, suppose that these are one-dimensional distributions. And suppose that I apply a phi to them to map them in two-dimensional space, such that each x becomes x squared, and each y becomes y squared. An original space, when I take the average of x's and take average of y's, they match each other, but they have different variance, right? So these distributions are not the same. But suppose that I applied a phi to them, and now they are in two-dimensional space. If I take the average of these two-dimensional points, compute the mu of them, and compute the average of these two-dimensional points, do they match? No. The first element, the mean is two-dimensional. The first element of the mean of these two will match, right? But the second element will not, right? Because basically the second element of this mean in two-dimensional space is the variance in the original space, right? So you go to two-dimensional space, you take the mean, but mean is basically the mean and the variance in the original space. So if they don't match, means the moments here doesn't match, right? Don't match. That's basically the intuition. But the idea is that there might be some sort of phi which take care of all of the moment of a distribution, not just the first and second moment. Okay? Maybe you can go to a space such that you have all of the moments. And if these two means are not the same, means that the moment of these two don't match. Okay? Now, the interesting thing is that in fact, you don't need to know this phi. Okay? Why you don't need to know this phi?
So, is the big picture idea that you have a bunch of test functions phi, and you're trying to capture the intuition that similar distributions yield similar expectations on a set of test functions?
Similar distributions have similar moments. I mean, if two distributions have the same set of moments, they are the same. That's basically the idea. Okay, suppose that I want to compute this quantity, and these are definition of these two means, right? So basically what I need to measure is 1 over n sigma over I phi xi minus 1 over m sigma phi yi, or let me put j here, squared. Okay, I can write it as 1 over n sigma I equal 1 to n xi minus 1 over m sigma phi yj transpose times 1 over n sigma phi xi minus 1 over m sigma phi yi. Now, if I expand this, I have this term, which is 1 over n squared, sigma I, sigma j, phi xi transpose phi xj. Then I have another term for this one, which is 1 m squared sigma I sigma j phi yi transpose phi yj. Then I have a cross term, which is minus 2 n times m phi xi transpose phi yj. Now, I have dot product here, phi transpose phi. Can be replaced by, sorry, a kernel, right? So I don't need to know phi. I can just put a kernel here. And this is also a dot product. I can put a kernel. So basically, I don't need to know phi. I just can rewrite everything in terms of kernels. Okay? So it can't be any phi. Phi should have some sort of properties if you want to prove this. Okay, it should be unit bound and some other properties. So not any kernel will do the job here, some specific kernels. One of them is RBF kernel, for example. RBF kernel maps the data in a Hilbert space infinitely long, and you can match all of the moment of two distributions. Basically, you just need to have some samples of two distributions. Then you can use this measure to compute the distance between two distributions. If you remember, KL divergence was not distance, was like divergence. It was not symmetric. This is symmetric. Okay, so it's really a distance. So if two distributions matches, it is 0. Otherwise, it's more than 0. So it's always positive, greater than equals 0. So you can basically measure similarity between two distributions using this measure. Okay? So this is called MMD. Now, generative model, the goal is to, you know the difference, I think, between generative models and discriminative models, right? So in generative models, basically, you would like to generate data. Okay? So generating data could be quite easy. If, say, for example, you're generating data from a Gaussian, for example. If I have a Gaussian distribution and I tell you, okay, generate a data for me, means that show me a data with a similar sort of property that I haven't seen in this training data. So you can sample from a Gaussian. You can find the mean and variance of this Gaussian, and we know how to sample from Gaussian. We know how to sample from uniform. We know how to sample from Bernoulli. We know how to sample from simple distributions, right? So this is my sample, and I tell you, okay, sample a new point for me, generate a new point for me. You know how to do it. But what if my samples are handwritten digits? I show you some handwritten digits, and I tell you, okay, generate a new one for me. Means sample. There's no difference between these two problems in nature, because this is also, that was a two-dimensional vector I wanted to sample from. This is higher dimensional vector, because I can just vectorize this. It's a long vector. Sample from this means sample this high-dimensional vectors in a manner that if I reshape it, it looks like a handwritten digit. It's a pretty difficult job, or it was a pretty difficult job up to a couple of years ago. So it was very hard to estimate the distributions of data like this, okay? Now, the idea of generative models in deep network is that suppose that I have a network. I know how to sample from uniform. I know how to sample from Gaussian. Can I feed this with a sample from uniform or sample from Gaussian such that the output look like an image, look like a face, a room, a building, whatever, you know? Give me a data. And the idea is that this network is a very complicated function. So I feed it with a simple uniform sample or Gaussian sample. And I expect this network to transform this data, this vector, to another vector, which when I reshape it, look like a handwritten digit or an image or whatever. Okay, that's the idea. Okay, to materialize this idea, basically, you know, suppose that we have chosen a data set that we want to sample from. Say it's MNIST, handwritten digits. So I have handwritten digits here, MNIST. Okay, so I can have a network, say it's feed-forward network. The input of the network is uniform or Gaussian. The output of the network, you know, I need to define an objective function. For the objective function, I'm going to define MMD as my objective function. Basically, I would say that, okay, the output of this network is one data set Q. And the original data MNIST is another data set P. And I want to minimize the distribution between P and Q. I want the distribution of this be similar to distribution of this, you know, and I have the tool for that, you know. If I have sample from P and I have sample from Q, then I can minimize. So train this network, change the weight of this network, such that the distribution of the output of this model matches the distribution of the data. And it's a very nice objective function. It's differentiable. I can take the derivative of that, and I can do backpropagation and train the weights. Okay? This is called moment matching generative model. That has been around since, I think, 2013 or so. Yes?
So I'm wondering, how do you pick a kernel that's good for all or most distributions?
You can't. Actually, in practice, they're playing with this kernel a lot. In fact, they're adding up some kernels.
Adding some?
Adding some kernels, you know. Because a kernel is a measure of similarity. You know, they have like RBF plus a polynomial plus some other type of kernels that they add them up.
Okay. So are they treating the kernel as some sort of basis functions, or?
No, why basis function?
I mean, it seems like you're taking linear combinations of kernels, or?
Yeah, linear combination of the kernels. These are not mathematical. It's like heuristic, you know, because some of the kernels, in some papers, you can see the type of kernels that they are using violate the theorem, you know, because theoretically it's supposed to be a kernel corresponding to a unit bound transformation. So, and they choose, for example, polynomial kernel, which doesn't satisfy this. Yes?
Is the discriminator of a GAN equivalent to a kernel?
No. No, we're going to actually talk about GAN now. Any question here? Yes?
Just going back a little bit. So you get, for example, a MNIST database, and you train it. And then what do you do with the trained net?
You know, this is MNIST, okay?
Yeah.
So I use MNIST as P.
Okay.
And I have 10,000 handwritten digits. These are the samples that I have from P. Okay, let me call it Q and call it Y to be consistent with what we have there. Okay, these are my samples from Q. My network, you know, I randomly set some weights here. and I fit it with a random Gaussian, a random uniform. It generates something, you know. Suppose these are samples from P. I would like to minimize the distance between P and Q. Q is fixed. You know, I don't change it. It's MNIST. So basically, it means that I have to change these weights until the distribution of the output of this network is similar to the distribution of MNIST. Okay? Yes?
How do you decide what kernel to use?
Just play with different kernels until it works.
Aren't you then overfitting your kernel to the?
Sorry?
Aren't you overfitting your kernel to the data somehow? I mean,
How do you overfit the kernel to the?
because you're finding a kernel such that you're minimizing the distance with whatever training data distribution you have, right?
Mm-hmm.
But the training data distribution is a bit different from the general distribution, right? So I mean, I don't know. Doesn't.
No, I don't think you know, if you think about this intuitively, not mathematically, you know, think of kernel as a measure of similarity, right? This measure basically tells me that, okay, the similarity between these two distributions is that how similar is the point with another point of this distribution, how similar is the point from the other distribution with the points of that distribution, minus 2 times of the similarity between these two. Okay, so I mean, intuitively it makes sense. You know, it's not clear that it's a measure of the similarity between two distributions, but in terms of a similarity measure, it makes sense that how similar they are, how different they are, right? So as long as it's a good measure of similarity, you should be able to produce something reasonable out of that, you know, as long as it's a, you know, for MNIST, for example, you know, let me give you this example. Suppose that this is one data point of a data set, and this is another data point. According to our perception, these two are pretty similar shapes. If you look at the Euclidean distance between these two, it's huge, right? Whenever it's black, it's white, and vice versa. So it has a big Euclidean distance. So if I compute RBF kernel on that, which is RBF is based on this Euclidean distance, it doesn't show any similarity between these two. It tells me that they are very dissimilar, but they are similar. They are similar based on my perception. You know, I have to choose a kernel which matches my task, matches my perception. So if in my task these two are similar, then this RBF based on Euclidean distance would be a bad kernel. It doesn't do the job. So you have to choose a kernel carefully that matches your intuition and perception about the data.
Standard kernels for image discrimination?
No. Okay. So that was about moment matching. So there's another way of making generative model. It's called adversarial network, or GAN, Generative Adversarial Network. That's the first paper that introduced GAN. It was 2014. It is very popular these days, you know. You see many applications of that, and just let me show you 2 quotes from Bengio and Yann LeCun. You know, LeCun believes that it's the coolest idea in the last 10 years, in the last decade in machine learning. And Bengio believes that this is basically the future of AI depends on this type of approach. Okay. So you can see many interesting applications that has used GAN. These are a couple of those, you know, a network which as the input, you know, you can have a network which as the input has uniform or Gaussian, and the output has the shape of a person or image and so on. But these are other type of applications, you know, a network that as input takes this type of labels and as output generate a realistic street view, for example. Or as the input takes, you know, a picture which has been taken by airplane or by a drone and make a map out of that. Or the input is, again, you know, this labels or schematic of a building, and the output is quite realistic. The input is black and white, and the output is colored. The input is just edges, and the output is, you know, a realistic image. Is day and the output is night, and vice versa is night and the day is any type of this transformation, translation in the image space, in the text space. You can see many interesting applications, and they use this technology. They use GAN. It's another example. These are not real pictures. These pictures have been generated by a network, but seems quite realistic. You know, the data set was data set of bedrooms, and these are some bedrooms that don't exist, but, you know, quite realistic. You may have heard, or I showed you in the introduction, that you know, in the space of words, you know, you can do arithmetic. You know, you can add like king minus man plus woman is queen. So in this paper, you can do the same thing in the space of images. This man with glasses minus a man without glasses plus a woman that's the output. Same woman with glasses. This is quite interesting. Caption to picture. So we have a description. We would like to generate, you know, this image has been generated out of this caption. You know, description is the orange on a table next to liquor bottle, and that's what the network generates out of this. Okay. The concept of adversarial learning is quite simple. You know, suppose that this is my generative model, you know, and I don't have this measure of similarity between two distributions. So I can be the judge myself, you know, if I can present, you know, I can just, if I have a way to take derivative of my judgment, then I can be the judge, and I can sit here and let the network to generate something and look at this image and say, no, it doesn't look like MNIST. Okay, change it. I can do that, but I cannot take derivative of my judgments. You know, change it means what? How can I back propagate my judgment to the network and let the network to, you know, correct itself? So adversarial network is basically the same thing, with the exception that you can't take derivative of this judgment. You know, instead of me be an inspector here, there is a classifier. You know, I put a classifier here. So I don't use, say, MMD, for example. A classifier is here, and the output of the network comes, and the classifier should tell me, should classify, should tell me that this is realistic or is not realistic. And how can this classifier understand that it's realistic or is not realistic? You know, I have a data set, MNIST. This is one class. I have the output of this model. This is another class. train a classifier which make distinction between these two classes, output of the network and MNIST. Suppose that it's a very good classifier. You have a very good classifier which can make distinction between these two. Then you let the network to train itself and make outputs which look like MNIST, so the classifier cannot make distinction between the output of the network and MNIST. Okay. Basically, the network tries to make itself better and better at the level that it can fool the classifier. So take this idea one step further. It's not a pre-trained classifier. It's a classifier that you're going to train during the process of training the network. So these two will be trained at the same time. Okay? And they are playing an adversarial game. This network would like to fool the classifier, would like to produce images in a way that classifier cannot recognize that it's fake. The job of this model, this generative model, is to make images such that the classifier cannot recognize it's fake. On the other hand, the classifier should make itself better and better at the level that it can, generative model can't fool the classifier, So classifier would like to detect any fake image. And generative model would like to make images such that classifier cannot detect it. So they compete with each other, And you train both of them at the same time. So that's the idea. The idea that you have real-world images like MNIST, and you take a sample, goes to a classifier, and you have a generative model, and generative model make an image, take a sample of that one. And this discriminator treat them as two classes, assign one to one class, say, for example, -1 to another class or 0 to another class. So one of them is real, the other one is fake. And you want to make this classifier better and better and better to make this distinction perfect. On the other hand, the generative should get better and better and better in a way that the discriminator cannot realize that it's fake. This latent is like this Z that goes inside the network, a sample from a uniform, a sample from a Gaussian, for example.
Why is it called latent?
Sorry?
Why is it called latent?
Correlated?
Yeah, it says latent random variable. So why is it called latent?
Latent random variable. A random variable here?
Yeah. Why is it called latent?
Oh, latent?
Yeah.
This is not a part of the network, It's your sample. If you you can think of your generative model as this model. This is your observation. Observation comes from a latent variable. Imagine that this is your model, that everything that I observe has been governed by a variable that I don't observe, right? Now, if I have the model, then when I sample from this, I can see one of these. But at the beginning, I don't see this. I just see the observation. I just see the MNIST. Okay, yes?
Can we go back to the previous slide? So what's the guarantee that the generative part of the network will be trained such that it will generate, for example, in MNIST, all the digits? It can always generate, for example, 2. And they are good 2s, and the network can fill the other part. But we are not training this to have all the examples.
No, if you have a data set that contains 10 digits,
Right.
you have another data set which contains only 2, a classifier can make distinction between these two classes, right? The idea is that classifier has no way to make distinction between these two. They're same. They're the same as they have the same distribution. Yes?
functions?
No, that's the objective function. I mean, next half an hour, I'm going to explain what this objective function is and how it works. Okay. So this is the objective function of GAN. The objective function basically is a min-max problem. We have a discriminator D and we have a generator G. And we are solving basically a min-max. Basically, given G, given the generator, we are trying to maximize this cost function and find a discriminator, a classifier, or the weight of the classifier, which maximizes this cost function. And given the classifier, D, we are minimizing this cost function, computing the weight of generator such that it's minimized. So the cost function is defined on this form. P of data is the real data, say, for example, MNIST, when I sample from MNIST. And P of Z is basically this Z. Okay? This is G. And this X would be G of Z, the output of the network. Okay. So, I have this generator and I have a discriminator. And I sample from MNIST. That's my real data, P of data. So I take a point from that. And it goes to discriminator. Discriminator tells me that, OK, it's 1. It's a real data. And I will feed the generator by a Z, like a Gaussian, a uniform, whatever. And GZ would be my new X. It goes to discriminator. Discriminator tells me that it's 0. It's fake. And then we have to change the weights until they match. Okay. And the claim is that by doing min-max, actually you can match the distribution of your real with the distribution of your generator. And we'll see how. Okay, so the idea is that take G as given, compute D as this max, then assume that the D is given, compute this mean, compute G, then assume that G is given, compute D, and go on until both of G and D are trained. Okay? So basically, you switch between these two. Okay. That's the cost function. That's our cost function. Let's just write the definition of expectation. Okay. Expectation of log dx with respect to p data is this integral. P data x log dx dx. And this expectation, by definition, is just this integral. Okay? Okay, now, this is my G. This is my Z. And this is G of Z, the output of the network. So X is G of Z. If X is G of Z, it means Z is G inverse of X, right, if it's invertible. And then dz, what is dz? Dz is basically G inverse prime, the derivative of G inverse at point X dx, right? So what I'm going to do is to replace any Z with G inverse X, any dz with G inverse prime X dx in this equations, in these definitions that I have. So the first term will not change. In the second term, whenever I have Z, I change it to G inverse X. Okay? And Gx, sorry, gz, I will change it to x. Okay, gz is x and z is g inverse x. So I would like to rewrite everything in terms of x. So I rewrite everything in terms of x here, and my dz basically would be just g inverse prime x dx. Okay, so I have everything here in terms of x. Okay, z has a distribution. It's Gaussian or it's uniform or whatever. Then g is a transformation applied to this z. I can compute the distribution of gz, right? So when I transform data, I can tell you what the distribution is after transformation, right? It has to do with the Jacobian of this transformation, right? So basically, that's exactly what we are doing here. We're saying that, G is a transformation applied to Z, and Z has a distribution, which we call it P of Z. But after transformation, the distribution of GZ, after transformation, would be basically this distribution times the Jacobian of G inverse because of transformation rule, When you transform a data, that's how you compute the distribution after transformation. So basically, P of the G inverse X times the Jacobian at point X, that's the distribution of Gx. So I call it PG, the distribution of generated points. So when I here, actually, from this step to this step, when I change all z to x, I have this term, I have this term, and I have this term. And this term times this term is basically distribution of generated points, PG. So basically, I just replace here PG log 1 minus dx. Okay, given G, this is, I have to maximize this cost function and compute D. Okay, so both of these integrals are over x, so I write it as one integral. It's P data x log dx plus P generated data log 1 minus dx. I have to maximize this with respect to D. Okay, so take derivative, set the derivative equal to 0. So if I take derivative, take of its integral, to understand it better, assume that it's discrete case, it's sum. You have sum of some terms, right? You're taking derivative with respect to a given x. So basically, you're taking derivative with respect to one of the terms of this sum, right? Okay, so here basically, if I take derivative of this log dx, would be what? Would be 1 divided by dx times P data. That's derivative of the first term. And derivative of the second term is PG divided by y minus dx.
Minus PG.
Sorry? Minus PG, sorry. And this is equal to 0. So dx times 1 minus dx, P data times 1 minus dx minus PG times dx is equal to 0. Now, I have to write here. It's PD minus PD dx minus PG dx is equal to 0. So dx is pd plus pg divided by, or sorry, is pd divided by pd plus pg, right? Okay. So if I take derivative and set it to 0, then dx is p data divided by p data plus pg. That's optimum d given g, right? So given g, that's the optimum d. Okay. Now let's get back to the cost function that we have. That was the cost function. Given g, we maximize for d, and we realize that optimum d has this quantity. Now, in this objective function that we took derivative and set it to 0, replace any d by the optimum d, and then optimize for g. You know, because that was the process. Assume that g is given, optimize for d, then assume that d is given, optimize for g. Now, I know that given g, the optimum d would be pd divided by pd plus pg. So I will replace every occurrence of d by pd divided by pg. So any of these d, assuming that it's optimal, it's p data divided by p data plus pg. Okay. Are you okay with this so far? Yes.
Sorry, question. So we assume that G is invertible, right? So doesn't that, in theory, doesn't that limit the kind of networks, the kind of activation functions you can use for G? Because, for example, ReLU is not invertible, right?
Yes. No, ReLU is not invertible, but you can assume that there is another network. I mean, this network is, ReLU is not invertible means that if you feed this network with Z and generate X, you can't use the same weight and put X inside and get Z on the other side. But it doesn't mean that there does not exist another network which take X and generate Z. You can't do that, right?
But I mean, I'm saying that you have to be careful to select the network architecture such that you make it invertible, right?
No, that's my point. No, go ahead and use ReLU, for example, here. It doesn't matter. So this network, you can't feed the network backward and generate G. But there is another network, L, that can take X as input and generate Z as output. And that L is basically the inverse of this G. You know? Is inverse of this G, but this G, when you say that ReLU is not invertible, you are right. But you are under the impression that G to be invertible, I should be able to feed the network backward and take whatever. No, it doesn't work that way. But there's another network which acts exactly as the inverse of this one. There's a network which can take X as input and generate Z as output. And you can train that one. And that's the inverse.
That's not the function inverse exactly. So it's not exactly the function inverse when you write G inverse?
No.
Okay.
No. Okay. No, I'm going to actually divide this quantity by 2 and multiply it by 2. Okay? So I'm only dividing this by 2 and then multiply it by 2. When I multiply this by 2, I have a log 2 here. Okay? So basically, there should be a 2 here. And then I have log of 1 over 2, which is negative log 2. And I have log of 1 over 2, which is negative log 2. So I add them up, and I put negative log 4 here. So basically, I divide these two by 2, and then I put negative log 4 here. Okay? Okay, before I show, I was not supposed to show this there. So what is this? It's KL divergence, right? KL divergence between P data and P data divided by P data plus PG over 2. And this is KL divergence between PG and the same quantity. Okay? So it's KL divergence between P data and this quantity. And this is KL divergence between PG and this quantity, minus log 4. And you would like to minimize it. Okay? KL divergence is always positive, or non-zero, basically. It's greater than equals 0. KL divergence cannot be negative. So this is greater than equals 0, and this is greater than equals 0. So if you want to minimize the whole quantity, what would be the minimum value? Sorry? No, the minimum of everything. Sorry? Minus log 4, right? Because the minimum happens when this is 0 and this is 0. Because they are greater than equals 0. And if you want to minimize this, the minimum happens when these two are 0, because they can't take any negative value. Okay? Okay, so the minimum happens when these two are 0. So the minimum is minus log 4. So the minimum happens when this is 0 and this is 0. And don't forget that KL divergence is measure of similarity, right? When KL divergence is 0, basically this one tells you that P data is the same as P data plus PG over 2. And this one tells you that PG is the same as P data plus G plus PG over 2. So when does this happen, the first term told me that P data is P data plus PG over 2. And the second term told me PG is P data plus PG over 2. When this is possible? Sorry? When PD is equal to PG. Okay? So it's possible if PD is equal to PG. That was our goal. I wanted to match the output of this, which is PG. I wanted to match distribution of this with this distribution. Okay? So by minimizing this cost function, given the optimum value of PD, then these two distributions will be matched. Yes?
The division over 2 to get to this, or we couldn't write the KL divergence before dividing by 2? I mean, you added that.
This is basically, this is symmetric KL divergence. By definition, symmetric KL divergence is KL divergence of P with respect to M and the KL divergence of Q with respect to M, because it's not symmetric, right? When M is P plus Q over 2. And that's exactly what's happening here. One term is P data with respect to M. The other one is PG with respect to M. And M is P data plus PG over 2.
But the factor of 2 is arbitrary, right? And we could have divided and multiplied through by any number we want.
Yeah. But then you were not able to show that it's equivalent to this. Right. Basically, we divided by 2, multiplied by 2 to show that by minimizing this, actually, we are matching this to M when M is average of these two. Yes? No? Okay. Okay, so by minimizing the cost function given D, given the optimum D, you are matching this to distributions. And the optimum D now is P D plus PG over 2. And if PD and PG are matched, PD plus PG over 2 is 0.5. Right? Is half, I decided this is in class 1, this is in class 1. Then it's 0.5, right? Okay, so in summary, this is our cost function. And we have a generative model, and we have a discriminative model. And we are looking for G such that G is the answer to this cost function. We are assuming that D is given, we compute G, and then we assume that G is given, we compute D. And we iterate between these two. And basically, this is similar to optimizing this cost function, means similar to matching these two distributions. Okay? So we don't have a explicit cost function to match two distributions. Through this classifier, actually, we are matching these two distributions. So instead of MMD that we're matching two distributions, we have this classifier that matches these two distributions. Okay? Okay, any question? Yes?
How would you categorize this method in terms of like the general types of learning? Like, is it supervised or semi-supervised?
It's supervised. Yeah. I mean, in supervised, adversarial by itself is not supervised or unsupervised. It's like if I ask the cost function is supervised or unsupervised. It can be used anywhere, right? It can be used in a unsupervised problem. It can be used in a supervised problem. It's just so let me show you a couple of examples. This is text to image, caption generate images. And if you want to have an idea of general structure of this type of networks, think of suppose that I have a network which take text and reconstruct text, like an autoencoder. And I have a network which take images and generate images, right? This take text, generate text, but at the middle, translate every text to a vector, a fixed length vector. And this one takes images, translate them to the same image, but at the middle, translate everything to a fixed length vector, right? If I take this part and this part and put them together, so the input could be X, the output could be Y. The only thing is that this fixed length vector may not match corresponding fixed length vector of this one. So you need another network here which map any fixed length vector of text to corresponding fixed length vector of image. So suppose that you have a data set of some captions and corresponding images. You train a network only on captions. You train a network only on images. even on images that you don't have caption for, even on text that you don't have images for. You know, you train this one, you train this one. Then you have a data set, a caption corresponding images. In this network, any caption translated to fixed length vector. In this network, any images translated to fixed length vector. Then I have a data set of captions and images. This vector corresponding to this text. This vector corresponding to this image. So if I put a network between these two, which matches this vector to this vector, then this, as the input, I give a text. As the output, I should get an image. You know, that's not how these models have been designed originally. That's sort of abstraction of many different papers that conceptually that's what's happening there, right? So it can do many different things. That could be this part and this part. You know, input is image, output is text. Input is text, output is image. This is English to English. This is French to French. This could be English to French translator. Could be French to English translator. Imagine just, you know, going from one domain to another domain. Language, text, image, whatever. Conceptually, that's what's happening. But every single image has a different recipe, you know, but conceptually, that's what's happening in the network. So it translates text to images. These images are fake images or images that has been generated by a network, but look like very realistic. Also, these flowers don't exist, you know. A description of flower. And, you know, it's just generated by a network. Okay. We learned about the variational autoencoder the other day, and variational autoencoder can be used as a generative model because variational autoencoder takes an input. It's autoencoder, and at the middle, you know, it's like a bottleneck. At the middle, you have a constraint that it should be similar to a Gaussian. Now, if I get rid of this part and sample from a Gaussian, the output should look like, you know, the data set that we trained with. So it is a generative model, variational autoencoder. This is variational autoencoder, and this is GAN. It's hard to see the difference. You know, these are right beside each other. The claim, actually, of GAN paper is that GAN, the points that generated by GAN shows more details are more realistic. Something interesting is that if you compare the likelihood of the data generated by variational autoencoder and the likelihood of the data generated by GAN, the likelihood of data generated by variational autoencoder is higher than the likelihood of GAN. But according to our perception, the quality of GAN is better than quality of variational autoencoder. I mean, the likelihood of variational autoencoder is higher because the objective function is designed for that. You know, we basically maximizing this likelihood, and it is maximum. We never maximize the likelihood for GAN. So it's more realistic in terms of our perception. In terms of likelihood, it's less. Yes?
Just going back a little bit, when you were talking about encoding the X intermediate vector and the Y intermediate vector, speaking, for example, in terms of text and images, as you mentioned, so I'm training the association of each vector from each text vector to each image vector. Is that you initially train on that, right?
Yep.
Okay. Just it, like.
Yes.
Without any RNN association?
No. You know, this is at conceptual level, you know.
Yeah.
It's not that you take this recipe and apply it somewhere and it works immediately. And if you look at the papers that translate, like, caption to image or image to caption. It's not as simple as what I explained. But that's an abstraction of many of these papers that do this type of translation from a language to another language, or from, image to another type of image. It's conceptually what's happening. Yes?
So if that is conceptual, wouldn't building an actual network to train, so to convert text like English to French and text to image vectors, wouldn't that actually account for domain adaptation, like domain knowledge? Like if this is just direct translation without this thing, conceptually, it would not be that good.
Domain adaptation basically, I think you know what domain adaptation is. You have a model which has been trained on a training set, and the distribution of your test set is different from the distribution of your training set. I gave you examples the other day. And there are models based on network for domain adaptation. And the idea is that you have a network, and basically you basically use another network as a transformation, which match the distribution of this with the distribution of your test set. And you can use maximum mean discrepancy to match these two distributions. You can use GAN to match these two distributions. Okay. These are some real images of CFAR10. These are some generated images using GAN of CFAR10. Try to match the distribution of CFAR10. Seems quite realistic images. And the source code actually for the original paper and the implementation for TensorFlow exists if you want to try. Any other question? Or any question? Okay. Thank you.